Hey guys, so I wanted to go over this with you real quick. I will attach this PDF, and there's 3 graphs. We'll go through this first one together, and then the second one will be bell work, and the third one will be like an extra credit bell work. I'll just add 10 points if you get it right. But okay, so let's look at this first graph. Notice we got displacement on the y-axis and distance on the x-axis. That's different than simple harmonic motion because we had time and we measured our period. But read the notes if you haven't read those notes yet. So this is for waves now. One wavelength can be measured from crest to crest or from trough to trough, and we denote wavelength with lambda. That's our variable, and then unit's going to be in some kind of length. It's a wave length, meters, centimeters, something like that. In this case it's meters. With this particular graph, things don't line up perfectly. Like you can tell, these are increments of 0.5, so it's not quite 6. And same, right here, it's a little bit more than, what would that be? A little bit more than 4. So what we can do is look at the cycles. So this starts at 0. This is 1 cycle. This is another cycle, and this is another cycle, and that's right at 10. So it makes 3 cycles, this time in 10, remember, in 10 meters. So our wavelength is distance for 1 cycle. The distance the wave moves in 1 cycle. So our wavelength, lambda, is 10 meters and 3 cycles. Ends up being 3.3 meters per cycle. So if you look, that's about 3.3. Makes sense right here. That's about 6.67. Wait, 5. Not there. Just kidding. That's about 6.67. Makes more sense. So that's our wavelength for this graph. And again, hopefully you've read the notes and you've seen that we have an equation. Velocity is the frequency times wavelength. And don't forget your simple harmonic equations. Those still apply. Frequency is 1 over the period. I don't think we put an equation for the amplitude. I mean, their amplitude is related to energy and things like that. But I think that's going to be beyond the scope of what we're going to cover, as long as you know that amplitude is related to the energy. It's how much energy is in the wave or simple harmonic motion system. But so, yeah, we'll use both these. So if we're given, we'll say the velocity is, 4 meters per second. Remember, make sure that this has to match up with this over here. They're both meters. So we'll say that. What's the frequency? Before, when we had our y-axis as time for the simple harmonic oscillators, we could just look at the graph and see the frequency. We can't do that here because we don't have time on either of the axes. So we're using this equation, f v is f lambda. If we just divide both sides by lambda to isolate the frequency, because that's what we're looking for, divide by lambda, we get frequency is velocity over lambda, which is 4 over 3.3. Let me grab a calculator real quick. You can calculate it yourself. That'd be pretty nifty. Comes out to be about 1.2. It's about 1.2. And what's our unit for frequency? Hertz, which is 1 over time. Which, if we look at the units of this, velocity is meters per second. Wavelength is meters, but since it's in the denominator, this goes times 1 over meters. Those cancel. The units is 1 over seconds, which is hertz. So you're going to do something similar for the second graph and the third one. The second graph, I'll give you a velocity and you find the wavelength from the graph. You're going to calculate the period this time. And then third graph, you'll calculate the angular frequency. But I will put that in the PDF, not this video. But there you have it.